In exercise 2319, we're going to make the same amines that we made in the last video. But the difference is, we're not just going to use reductive amination. In the first step, we're going to do the Gabriel synthesis. So we'll start with phthalimide. You might remember the first step in the Gabriel synthesis is to combine phthalimide, which has this alpha position with an acidic hydrogen, with a base, like potassium hydroxide. The OH and the H leave as water, and what you end up with is the positive potassium and the negative phthalimide kind of sticking to each other as a salt, which is just an ionic compound. Two things sticking together because of their opposite charge. That's called potassium phthalimide. Potassium phthalimide is what you have after this first step. And so that's what they're talking about here when they say starting with potassium phthalimide. But just to be consistent with what we did before, we're going to start with phthalimide and add the potassium hydroxide as our first step. That's going to be our first and original source of nitrogen, and we'll use the Gabriel synthesis to create the first bond from nitrogen to carbon. One important thing to note about the Gabriel synthesis is it will only allow you to make primary amines. Those are amines that are bonded to only one carbon. So if you want to make a secondary amine, which you do here, this nitrogen is bonded to 2 carbons. In that case, you can only add the first carbon using the Gabriel synthesis. Every carbon after that has to be added using reductive amination. So if we take this molecule, we're going to play a similar game as what we played before, where we're going to break the bonds between carbons and the nitrogen. Here, instead of starting with ammonia, the nitrogen will come from phthalimide. But as for the carbon chains, you want to look for the one that's less bulky, and that one you want to redraw as an alkyl halide. That's the one that you're going to use in the Gabriel synthesis. Because remember, the Gabriel synthesis is an SN2 reaction, and so it'll work best if the substrate is not crowded, so that the nucleophile has room to swoop in and attack and kick the leaving group off. But let's finish looking at these different groups that we have. We really have 3 different groups here. The nitrogen is going to come from phthalimide, so we can erase that. Now where the nitrogen was, we have 2 branches. On the less crowded branch, put a halogen. I'll put bromine, but it could just as well be chlorine or iodine. We're going to use that in the Gabriel synthesis. On the more crowded branch, where the nitrogen was, add a carbonyl. We're going to do reductive amination on that molecule. Okay, so here we have our standard recipe for the Gabriel synthesis. You always start with phthalimide. Potassium hydroxide you always add to rip that alpha hydrogen off, turn the nitrogen into a nucleophile. And then you always add an alkyl halide. Well, we just figured out the alkyl halide that we want to add. Here it is this ethyl bromide, or bromoethane if you prefer. That will create a carbon to nitrogen bond. And then in the third step, you would either hydrolyze the nitrogen from the phthalimide with an acid, or you would release it doing a nucleophilic acyl substitution with hydrazine, as we've seen in previous videos. What you would end up with after that first step is whatever alkyl halide you have, but instead of the halogen, you'll have the nitrogen. So you create an amine, but it's a primary amine. It's only bonded to 1 carbon. The nitrogen is only bonded to 1 carbon. So we've created part of our molecule, but we still have another branch, this blue branch, to add. If you're trying to make something more than a primary amine, then you have to use reductive amination. So you'd take the aldehyde that we figured out above, and you would add the amine we created using the Gabriel synthesis, And if that is in the presence of the aldehyde, and you include an acid catalyst and a weak reducing agent like sodium cyanoborohydride, NaBH3CN, the acid, aldehyde, and amine will create an imine, I-M-I-N-E. And then that will be reduced by the sodium cyanoborohydride to an amine. So that the overall effect is where the double bond to the oxygen was, you'll have a single bond to the nitrogen. I'm going to erase this hydrogen. It is still there. It's just implied in the skeletal structure. Oops. And there we have it, our molecule that we wanted from the very beginning. So what we did was we first did the Gabriel synthesis, and that was 3 steps. We have phthalimide, we added potassium hydroxide, the appropriate alkyl halide, and either hydronium or hydrazine. Either one, not both. Once you do that, as a 4th step, you would add the amine you make with the aldehyde we figured out in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, and that will give you your product. So this would be the synthesis. Okay, let's think about that same sort of procedure for B. Now we know that the nitrogen source is going to be phthalimide. So the nitrogen will come from phthalimide. Let's think about this molecule. The nitrogen is going to come from phthalimide. The carbon will come from the alkyl group in the alkyl halide. So actually, while I have this out, let me give the general form and include that for the rest of these. We know that we want to start by doing a Gabriel synthesis for each of these. So we'll have that recipe available in each one. Okay, so we'll go back to this one we were working on just now. The nitrogen is going to come from phthalimide. The carbon chain, and here we only have one, so we're trying to make a primary amine. That carbon chain will be the R group in the alkyl halide. So to figure out the alkyl halide, all we have to do is take the amine we have and replace the nitrogen with a leaving group. You could use chlorine, bromine, iodine, any leaving group will do. So when you do this reaction, the hydrogen of phthalimide will get ripped off by the strong base, the potassium hydroxide. The electrons in the bond will snap back onto the nitrogen, which then acts as a nucleophile. It would attack this carbon here and kick the bromine off, doing an SN2 reaction. Now you'd have a bond between the nitrogen and the carbon. And then you just release the nitrogen from the claws of the phthalimide, either by adding an acid catalyst and doing acid catalyzed hydrolysis of an amide, or by doing nucleophilic acyl substitution with the hydrazine. The overall result of this reaction is that the nitrogen would take the place of the bromine. And in this case, because we wanted a primary amine, that's all we'd have to do. This is the full synthesis for the compound we have in B. Okay, let's try to do C. Now in C, first step is take your molecule and break any of the bonds between carbon and nitrogen. So we've got 1, 2, and 3 of those. Now let's think about the different pieces that we're going to have to connect. We have this 5-membered ring to the left, we have the nitrogen in the middle, we have a methyl group at the bottom left, and we have a methyl group at the top right. Methyl groups at the bottom right and top right. Okay, well, we know the nitrogen is going to come from phthalimide. One of the carbon chains will be attached as an alkyl halide in the Gabriel synthesis. We're going to choose the least crowded chain. So we sort of have 4 pieces here. I'm going to copy this, and I'm going to copy it 3 times. I'm not going to copy it 4 times because the nitrogen is going to come from phthalimide. So we can erase the nitrogen. Oops. Erase the nitrogen. That nitrogen will be coming from phthalimide here. Okay. As for the other 3 pieces, let's think about these one at a time. One of the least hindered ones, the least crowded ones, so either the green or the blue one, I'm going to choose the blue one. That one, attach a leaving group. So I'll have bromine here. That will be the halogen that we can use in the Gabriel synthesis, the alkyl halide that we can use in the Gabriel synthesis. Okay, so much for the blue one. Now, for the others, we have to attach using the reductive amination. So where the nitrogen, well, let's first think about the purple one. Where the nitrogen was attached, add a carbonyl. And then likewise for the green one, where the nitrogen was attached, add a carbonyl. In this case, we have formaldehyde, the smallest possible aldehyde. Okay, so we took our original molecule, we broke any bonds between nitrogens and carbons. The least hindered carbon, the least bulky carbon, we used as an alkyl halide in the Gabriel synthesis. And the result of this synthesis is that we would have the same alkyl halide, but instead of the halogen, it will be attached to the nitrogen. That gives us a primary amine. And once we have a primary amine, we can add the other 2 bonds to the nitrogen, between the nitrogen and the carbons, by doing reductive amination. So we can take one of our ketones, or our aldehydes, it doesn't matter which one. We can take the amine we made from the Gabriel synthesis. Oops. And if we combine those, the amine and the ketone, in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, NaBH3CN, then what we end up with is, at first we'd make an imine, and then we'd reduce it to an amine, so that ultimately, where the carbonyl was attached, a nitrogen attaches instead. And so now we've formed 2 of the bonds between the nitrogen and carbons. We just have to add the 3rd group, the group that we had in green. So we take that formaldehyde and we treat it with the amine that we made in the previous step. And if we mix that with the carbonyl compound, in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, NaBH3CN, then at first we form an imine in the presence of the acid catalyst, and then afterwards, once we have the imine, we reduce it using the weak reducing agent, so that overall, where the carbonyl was attached, instead, we have a nitrogen. Now those hydrogens are still there, but I'm going to erase them because they're implied in this skeletal structure. And so we've made our tertiary amine. You'll notice that this molecule is the same one that we wanted to make at the very beginning of this exercise. Okay, so overall, our synthesis is, first, we'll use the Gabriel synthesis. We'll start with phthalimide, treat it with potassium hydroxide, the least hindered alkyl halide that we can make, and then either hydronium or hydrazine. In the second step, well, really the fourth step, we'll take the amine we made and combine it with one of the aldehydes or ketones that we know we needed from the original molecule. We combine it in the presence of an acid catalyst and a weak reducing agent, and that gives us our secondary amine. And then in the fifth step, we would take that secondary amine that we made in step 4, combine it with the aldehyde that we know we need to add still in the presence of an acid catalyst and a weak reducing agent, and that gives us our final product. So we're using both the Gabriel synthesis and reductive amination to make a tertiary amine. Okay, let's try it with D. Now we know that we want to use the Gabriel synthesis. They ask us to. Well, they don't say the word Gabriel synthesis specifically, but they say the word use phthalimide as your nitrogen source. And so that's essentially saying use the Gabriel synthesis. Now to use this, we're going to look at our molecule, and any bonds between a nitrogen and a carbon we're going to break. Let's think about the different pieces here. We have a carbon chain on the left, we have the nitrogen, and we have a carbon chain on the right. Those are our 3 separate pieces. The nitrogen is going to come from phthalimide, so we can erase that. After that, we have 2 pieces, so I'm going to copy this. Let's think about the purple one, where the nitrogen, now both of these are equally crowded, so where the nitrogen was attached, we'll put a leaving group, and that can function as our alkyl halide in the Gabriel synthesis. For the blue one, now we can only use the Gabriel synthesis to make a primary amine, so to attach the second carbon chain, we'll have to use reductive amination, and so in this blue group, where the nitrogen was attached, we'll put a carbonyl. Okay, so as always with the Gabriel synthesis, we start with phthalimide. Potassium hydroxide rips the alpha hydrogen off, leaves us with a nitrogen nucleophile. That attacks the alkyl halide in an SN2 reaction, kicks the bromine off, and now we have a bond between the nitrogen and this carbon instead. Then we release the nitrogen from phthalimide by doing an acid-catalyzed hydrolysis of an amide, or just a nucleophilic acyl substitution with hydrazine. One or the other, but not both. The result of it all is that we have whatever our alkyl halide is, but instead of the leaving group there, we have the nitrogen that came in as a nucleophile. So that's the result of our Gabriel synthesis. But we still want to add another carbon chain on here. So we take the aldehyde that we figured out we needed. We're going to add this new bond between the nitrogen and a carbon using reductive amination. To that aldehyde, we'll add the amine we made in the previous step. And if we add that to the aldehyde in the presence of an acid catalyst, it will turn into an imine. And then we can reduce the imine, which has 2 bonds to the nitrogen. We can make it just 1 bond to the nitrogen using a weak reducing agent like sodium cyanoborohydride, NaBH3CN. And that'll give us an amine. So that ultimately, the overall effect is where the carbonyl attached, you erase it, and you add a nitrogen. And that hydrogen is still there, but I'm going to erase it because it's implied in the skeletal structure. And you could see that what we have at this end step is the same structure that we wanted in the very beginning. So blue, purple. So ultimately, the synthesis for this has several steps. we have the first three steps are the Gabriel synthesis. That makes a primary amine. And then as a fourth step, we'll take the amine we made from the Gabriel synthesis, combine it with the aldehyde that we knew we needed from analyzing the original molecule, and combine that with an acid catalyst and a weak reducing agent like sodium cyanoborohydride. And that synthesis will give us our product, diethylamine. Okay, let's think about E. Now they tell us that we want to make this amine using phthalimide as our nitrogen source. And so we know that we're going to have to do the Gabriel synthesis. So I wrote out so we have here the general formula, the general recipe for a Gabriel synthesis. Now if we look at our molecule, when you're trying to work backwards and think of what you need as separate pieces to bring together to make this amine, break the bonds between the nitrogen and any carbons. And think about how many pieces you have. We have an ethyl group to the left, we have an ethyl group going down, we have an ethyl group going to the right, and then we have the nitrogen. And so we have 4 pieces there. Now the nitrogen is going to come from phthalimide. So we can sort of disregard that. But after we get rid of that, we still have 3 carbon chains that we need to think about. How will we attach each of those carbon chains to the nitrogen? Well, the first one, and these are all the same chain, but if they weren't, you would choose the one that's the least crowded. The first one needs to be added in the Gabriel synthesis. We need to make an alkyl halide. We could use any of these to do that. I'm going to use the purple one. Where the nitrogen was bonded, we'll put a leaving group like bromine. It could also be chlorine or iodine. Now that's the only one that you can attach using the Gabriel synthesis, because the Gabriel synthesis because it's an SN2 reaction, it can only work to make, a primary amine. It's partly because it's an SN2 reaction, but it's partly because this nitrogen in phthalimide is bonded to 2 other groups. And so it only has 1 hydrogen that it can use to do this SN2 reaction. And that's why you can only make a primary amine with the Gabriel synthesis. Now we've seen how the effect of the Gabriel synthesis is you have whatever alkyl halide you started with, but instead of the halogen in the end, you have the nitrogen, so that you create an amine. Okay, so that will be our first procedure. We create that primary amine. So that's how we're going to attach this purple group. Now let's think about the other groups. After that, to make a secondary or tertiary amine, we're going to use reductive amination. So let's think about this blue one, where you had the bond to the nitrogen, draw in a carbonyl. Likewise for the green one, where you had the bond to the nitrogen, draw in a carbonyl. Those are the 2 aldehydes or ketones, here they're both aldehydes, that we need to make our final amine. So we can use the first one, and if we combine that with the amine we made in the Gabriel synthesis, and we use an acid catalyst and a weak reducing agent like sodium cyanoborohydride, NaBH3CN, then the effect is that where the carbonyl was, you attach the nitrogen. I'm going to erase this hydrogen. It is still there, but it's implied in the skeletal structure. So now we have a secondary amine. We want a tertiary amine, so we can take that last aldehyde that we know we have to add, and we can combine it with the amine we made in the previous step. Oops. And if we do that in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, NaBH3CN, then the overall effect will be to replace the carbonyl with a bond to the nitrogen. I'm going to erase this hydrogen. It is still there, but it's implied in the skeletal structure. So you'll notice that what we have at this point is our tertiary amine, triethyl amine. So that overall, our synthesis involved several steps, really 5 steps. The first 3 steps were the standard steps for the Gabriel synthesis. We took phthalimide, ripped the alpha hydrogen off with potassium hydroxide, did an SN2 reaction with an alkyl halide that created a connection between the nitrogen and the carbon of one of the chains, and then we released the nitrogen from the claws of phthalimide, either by using an acid catalyst, so acid catalyzed hydrolysis, or using hydrazine, one or the other, but not both. And that gave us our primary amine. To make our secondary amine, in this 4th step, we took the amine we made previously and we combined it with an aldehyde that we got from analyzing the original molecule. And if we did that do that in the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, that gives us our secondary amine. And then in a 5th and final step, we can take our secondary amine, combine it with the last aldehyde that we need to add on. In the presence of an acid catalyst and a weak reducing agent like sodium cyanoborohydride, that gave us our final product. So, overall, that is the synthesis for this amine, using the Gabriel synthesis followed by a couple reductive aminations. Okay, last one for this video. They say that we want to use phthalimide, potassium phthalimide, as our nitrogen source. So we know we're going to have to do the Gabriel synthesis. If we take this molecule, so we know we're going to have to do the Gabriel synthesis, and I have the recipe for that here, general recipe. And we can take this molecule, and if we're going to make this with phthalimide as our nitrogen source, then we have to form all these bonds between these nitrogens and these carbon chains, because those don't exist in the original nitrogen source. So thinking backwards, break each of those, and then you'll have a sense of the pieces that you need to bring together. Now here, the nitrogen is going to be one of the pieces. We have a carbon chain to the left, we have a carbon chain to the bottom right, and we have a carbon chain to the top right. Now the nitrogen is going to come from phthalimide, so we'll ignore that, and after that we still have 3 pieces we have to consider how we're going to attach. So let's think about those one at a time. The first one we have to think about is which carbon chain is going to be the alkyl halide in the Gabriel synthesis. That will be the least crowded of the carbon chains. You could see that that's the blue one here. So I'll erase the more crowded ones. The blue one, where the nitrogen was attached, I'm going to add a halogen, a leaving group. It could be chlorine, bromine, or iodine. That's the halogen that we'll use in the Gabriel synthesis. We want it to be the least crowded one because the Gabriel synthesis is an SN2 reaction. And the least crowded it is, the more efficiently the nucleophile can swoop in and kick the leaving group off. The overall effect of the Gabriel synthesis is that we take whatever alkyl halide we have and we replace the halogen with a nitrogen, the nitrogen from phthalimide. And so we form a primary amine. The amine is only bonded to 1 carbon, so it's a primary amine. So we've attached that blue group. We can erase that from our analysis. We still have to attach the purple and green groups. We're going to have to attach these using reductive amination. So first, the purple group, where the nitrogen was attached, draw in a carbonyl. And then for the green group, where the nitrogen was attached, draw in a carbonyl. So in this case, we have 2 ketones. Now we can form a single bond between these carbon chains and the nitrogen by doing a reductive amination. First, we'll turn that ketone into an imine by combining the ketone with an amine, a primary amine, in the presence of an acid catalyst. And then once we have that imine with 2 bonds between the carbon and the nitrogen, We can reduce it, so there's only one bond between them, to an amine using a weak reducing agent, like sodium cyanoborohydride, NaBH3CN. And we discussed what each of these things is doing and sort of the background in it in a previous video. Now the overall effect here is that where the carbonyl was, you'll replace it with a bond to the nitrogen. And so now we have a secondary amine. The nitrogen is bonded to 2 carbons, so it's secondary. Okay, now we still have to attach one more carbon chain, so we can take the ketone that we figured out we needed earlier, and we can do another reductive amination. We can take the amine, the secondary amine that we just formed, and if we treat that amine with the ketone in the presence of an acid catalyst, we would actually end up getting an enamine. But then if you reduce that with a sodium borohydride, or, sodium cyanoborohydride, NaBH3CN, then you'll end up with your tertiary amine. The effect is that where the carbonyl was, you'll replace it with a bond to the nitrogen. And so you can see that at the end here we have the molecule that we wanted at the very beginning, the tertiary amine that we wanted to make. So overall, the synthesis to create that molecule, that beautiful work of art, was first we did the 3-step Gabriel synthesis. We treated phthalimide with potassium hydroxide. That turned the nitrogen into a nucleophile. Then it attacked this carbon here and kicked the leaving group off in an SN2 reaction. That created the nitrogen to carbon bond. Then we released the nitrogen from the clutches of phthalimide, either by using an acid-catalyzed hydrolysis of an amide, or by using hydrazine and doing a nucleophilic acyl substitution. That gave us our primary amine. And that's the only thing you can make with a Gabriel synthesis, is a primary amine. To make our tertiary amine, nitrogen bonded to 1, 2, 3 carbons, to make your tertiary amine, we'd have to do the reductive amination. So we took the ketone, one of the ketones we figured out we needed, we added the amine we made through the Gabriel synthesis with an acid catalyst and a weak reducing agent, and we got our secondary amine. And then we took our secondary amine, combined it with the other ketone we saw we needed, and an acid catalyst and the reducing agent, and that gave us our tertiary amine. So in this video we've seen how you can make a primary amine using the Gabriel synthesis. You can use phthalimide as a source of nitrogen atoms. And once you have the primary amine, you can make it a secondary or tertiary amine using reductive amination.